All right, let's go have a chat with Dr. Mark Wang, who's going to tell us about how he's using neuromorphic technologies to learn and create computers that think.
Hello everyone, my name is Mark Wang and I'm a neuromorphic engineer here. So my research is neuromorphic engineering, deep learning, integrated circuit design. So my main research interest is investigate how the brain works and what we can borrow from the biological systems, and whether we can use that principle to build a better computer for everybody can use. And another particular research interest is to fight with the climate change, because people know all the server farms, they are power hungry, they consume a lot of power, maybe 1/3 power of the whole global consumption. And if we can work on that, use the neuromorphic computing to replace the conventional server farm, we can reduce the power consumption a lot.
So Mark, why will looking at how biology works in neuromorphic engineering, why will that reduce the power and help with climate change?
That's a very good question. So you see, our brain consumes about 20 watts, and it can do a very good job for the sensory perception tasks and whatever. But this will, in turn, if we use a GPU to do the same job, it costs 100,000 watts to do the same job. And that's the main difference. So if we can borrow the biological principles to process all this data, we should be able to reduce the power consumption a lot. So these are the spiking neuron processors we have designed 2 years ago. So it can be used to simulate up to 1 billion spiking neurons in real time.
So it's basically a model of the brain on a silicon chip.
Yes, exactly.
And you designed that?
Yes, I designed that.
You laid every transistor out?
Well, not exactly. I let the tool to do it for me. It's 130 nanometer process. It's not a state-of-the-art process, because as a university research lab, we are more interested in the computing architecture instead of using some fancy technology. But the design can be ported to the state-of-the-art process like 5 nanometer. Currently, we are working with Intel, and we are working some large-scale spiking neural networks platforms. In the left, in the window, what you see is the waveform, what we call it. So it tells we know the silicon chip have the clock cycles. So this tells the signal what they're doing on each clock cycle. And the other side is the code, because the circuit become bigger and bigger. So we use the HDL, hardware description language, to describe the circuit.
All right. Now, let's go have a chat with Dr. Ying Zhu about how we're using neuromorphic techniques on audio to build biologically inspired systems that can hear.
Hello everyone, I'm Ying. I'm a postdoc working on neuromorphic auditory system, hardware implementation and application. What I'm doing here is I'm building circuits to mimic how humans and animals perform auditory perception tasks and apply those for practical applications. Here example of a cochlear circuit running on a hardware platform, FPGA board. Here we can see this is the input sound on the top, which is my voice now, and the bottom window shows the image of the sound. This is a cochlear chip, and I'm trying to apply this cochlear chip on multiple applications, for example, sound localization and acoustic scenes classification. And also, I'm trying to apply those for practical applications and place this device to portable devices for multiple environment usage.
So, Ying, how does this big board over here relate to your little chip over here?
Oh, this is you can see this as a verification platform. So I'm just prototyping all the circuits on a FPGA board because it's commercially available. It can be easily programmed on the FPGA and verify all the functions. And when I'm sure everything is ready, I just use the same design for a chip implementation. This can be used under various environments. For example, think about in some scenario, human can't reach, very deep underwater or remote forest. But since we have this hardware ear, we can place the ear there and collect data and do some analysis.
Thank you so much.
Thank you.
Now to change tact a little bit, let's talk about some neuromorphic applications. I'm going to start off talking about one of our most exciting applications of neuromorphic cameras, how we're putting them into space. So, our project to put these cameras in space is called Falcon Neuro. And the goal of Falcon Neuro is to put 2 neuromorphic cameras onto the International Space Station to look for a very special kind of atmospheric phenomena called a sprite, or transient luminous event. Now, to tell you what these are, I'm going to show you a video of the Earth from the International Space Station. And what you see here is all the lightning storms. Lightning hits the ground all the time from the clouds. Now, occasionally, however, the lightning doesn't go down from the clouds to the ground. It goes from the clouds up into the upper atmosphere, as you see over here. This is called a sprite, or a transient luminous event. And they're kind of rare and really, really fascinating, a little understudied. And the interesting thing about them is we don't really know what they do to the atmosphere, how they're going to affect high-altitude aircraft, or our satellites, or communication systems. And there's a lot of research that needs to be done to figure out how often these things happen and what their effects are going forward in space. Now, event-based cameras, neuromorphic cameras, the silicon retinas we build here in the lab are perfectly suited for this task because they're really good at capturing high speed and very bright events. Now, these sprites are really fast and very high and very hard to see from the ground. So we have a unique opportunity to put these on the International Space Station and look down and figure out how often these happen on the Earth's surface and whereabouts they happen. So what we're going to build is this. This is Falcon Neuro. It's a module with 2 event-based neuromorphic cameras in it that's going to be installed on the International Space Station. It has one camera that looks at the horizon and one that looks directly down. Now, there's some really, really big advantages to putting these things on the International Space Station as opposed to a CubeSat or a little satellite in space. In that if you put a satellite up, it's very hard to do anything with it. You basically just wait for it to come back to Earth and burn up in the atmosphere. Whereas if you put something on the International Space Station, you actually have astronauts up there who can look after it. You don't have to worry about power, you don't have to worry about communications. It's a really, really, really exciting research opportunity. And we are building this in the lab here. And just in a moment, we're going to go talk to one of my colleagues, Paras, who's going to show you the actual equipment that we're building and putting into space. Just to give you an idea of where this thing is going, it's going on the Columbus module of the International Space Station. Now that little part circled there in red, it's actually where the spacecraft, like the Dragon, Falcon 9 rocket and Dragon, just the Dragon, will dock with the International Space Station when bringing this device up into space. Now I'm going to show you what a sprite actually looks like. This is a recording of a sprite from a high-speed conventional camera. Now you can see from the time up there that's going up in tiny, tiny increments. This is extremely fast. And this is captured, this is probably one of the best recordings I've seen captured from the ground. And what you'll see, it almost looks like an orange explosion. It's called a carrot spider because it's carrot-like in shape. And you can see it has these weird tendrils that go up. You'll see it in a second over here. And this is the phenomenon we really want to study. We'll use these cameras to figure out how often this happens and what the effects are on spacecraft and the environment. So without further ado, let's go talk to Paras and we'll show you what this equipment looks like. Paras.
Hi, I'm Paras Gaki. I'm technical officer and working on ISS model. On this one, we are putting a camera over there, and this is the actual camera that goes in the ISS station. And I want to quickly show you how it's captured on this one. So this is the live footage coming from the camera right now.
So this is a live feed from the camera, from the neuromorphic camera that will go on the International Space Station. But this isn't how we're going to run it when it's in space, because we have to record as it goes around and transmit it back to Earth.
Yes, exactly. You do that. So we are putting the two camera over there, and so it will be capturing one at the looking at down to the Earth, and another looking at the horizon on this one. And basically, I want to show another video one, which is the recording of that previously did one. So this is in a 3D visual where we can see. So basically, I have created one video moving a hand in front of it. So I'll just look back again to see in a 2D visualization. Basically, we'll be putting two cameras on the Columbus model. It will be somewhere around here. So this is the real size, actual size of the model that goes in the Columbus one. But the eyes is really small compared to this one.
I have to contact Lego and ask
Yeah, so basically it will have like 3 sections on this one. So the bottom section will be have like all the PCBs, the control system on that one, and the top will be like to the two cameras. So we can see one hole from the top camera. So we'll basically there will be like even base camera on this one. You can see it from the top also. We have already one camera fitted on that.
Excellent.
And this is the inner section where the other camera goes on. So basically one will be looking at this direction and other will be looking on the other direction, somewhere like in 70 to 75 degree.
And this is scheduled to launch in November next year.
Yep,
Well, Paras, thank you so much.
no worries.
Fantastic, really
Glad to help.
appreciate it. So, Paras is working on Vulcan Neuro, and that's where he sits and does all the testing. But let me show you where he actually builds the hardware. Let's give you a tour of the workshop where all the magic happens. Peek behind the curtain, take a look and see where we keep all the equipment and where we do all the work that goes into making these projects a reality. And this is our workshop. It's a full electronics and mechanical engineering workshop. We have soldering stations, 3D printers, places to test microchips. We have lots of space for students and postdocs and interns to work. And I'll show you a few of the interesting things we have around here. What you might notice along the far wall over there is something called the toaster, which is our drone simulator. And the reason we simulate drones is that the problem with drones is they're actually quite hard to fly, and you can't fly them indoors. And with this, we can test all sorts of algorithms for making drones that can dodge obstacles, for example, without having to actually fly them. We can move it by just pulling those strings, for example. This is one of our summer intern projects, for example. Over here, we have a pan tilt mount that simulates how head motion works. In that box over there, you'll find a camera, and one of our interns is busy looking at how temperature affects these cameras, and that's really important for our space missions, because it's very hard to get rid of heat in space. And if you come over here, what you'll see is, it looks like tomato plants, or fake tomato plants, but that's exactly what they are. And one of our students is busy looking at applications of these cameras in agricultural settings, especially using color to see if we can find ripe fruits amongst leaves, which is actually a really hard problem. So that's just an idea of some of the interesting projects we have going on in our workshop. This is where all the magic happens, I suppose. Let's leave the workshop so people can actually get their work done, and we'll head back into the main area. Let's go and look at some more of the really interesting applications for these cameras. And we're going to start with Dr. Moritz Milde, who's going to talk to us about a really exciting application for these cameras underwater. So let's cut to Moritz now.
Thank you, Greg, and also welcome from my side. You just saw that we can shoot for the stars and use neuromorphic cameras to observe the sky, detect satellites, and track space junk. Now we will dive together underwater and see what we can detect using neuromorphic cameras in our ongoing project Deep Blue. In this project, we aim to use the amazing features of neuromorphic cameras to detect air bubbles, fish, and other sea life. But more importantly, we aim to detect event patterns produced by wave motion and marine pollution. This is a very challenging task using conventional cameras, as motion leads to blurred images, especially underwater where we don't have much light. This will help us to clean up our ocean, but it will also enable us to detect the stars and the moon through the water surface. You may wonder, why do you need to do this? If we go from our home to our holiday destination, we use Google Maps and GPS to know where we are and to know where we need to go. If we dive underwater, however, GPS doesn't work anymore. If we can detect the stars and the moon and know their position, we can calculate our position anywhere on this planet. We are at the very beginning of this exciting research adventure. We built our first prototype, and we were able to see air bubbles produced by me at home in my bathtub rising to the water surface. In a second experiment, we were able to see through the waves as we submerged the camera in water, as you can still see me and the background tree as the waves are breaking over the camera. We are thrilled to go down this novel research avenue to understand the capabilities of neuromorphic cameras underwater. Thank you so much for your attention, and have a great day.
That is exciting, Moritz. Thank you. All right. Let's take a little walk over here and talk to one of our PhD students, Yesh, about a really exciting project.
Hello everyone, I'm Yashwant, and I'm a PhD student at ICNS, the Marx Institute. So this is a pinball machine. So it's a really old, refurbished mechanical pinball machine that we have tried to come up with a robotic pinball machine just using the old ones that we used to have at the old arcade shops. So this has a variable lighting system, a LED system which can change the intensity of light falling on it, and there are a couple of flippers, as you might already be familiar with a pinball machine. And then we have a neuromorphic camera up there, which is looking directly at the board, and we try to run it using the camera as a vision system.
So what about it is roboticized?
So the flippers are completely automatic. We can use a laptop or a PC to run them whenever you want. The entire thing is continuous, so you constantly get the feed from the neuromorphic camera, and then you can use that feed to process the information and then actively act on the board.
What about pinball makes it a good problem to solve?
Two things. So one, you need to be really fast to solve or to play pinball, because you're constantly having a fast moving object and you need to act in real time. And second thing, it's quite simple. You just have two flippers. You either flip right or left whenever the ball reaches the bottom, and then you try to score as much as possible.
So because it's pinball, you have a score.
Yeah,
And I guess the better you score at pinball, the better your algorithm is at playing pinball.
exactly. And the best part, we can let humans, I mean us, play the pinball, and we have recorded the score, how much we can score on the table, and then we can match those scores against the ones that we are trying to develop here, the algorithms which are going to, if we're going to see if those scores match, if we can beat humans or not.
So we can compare algorithms with other algorithms and algorithms with humans.
Yes.
Exactly. That's a fantastically
Yeah.
interesting way to look at it. So tell me a bit about the box. What does the box do, and why do we have these very dramatic curtains?
Yeah, so we have a lot of things going on around here. We have a light system which can change, and we have different lighting conditions that we want to control and test all these algorithms at different parameter levels. So we would like to conceal the entire, we use these curtains to block any outside light, so that we can have a perfectly controlled environment where we can control the different variations in the lighting environment, and then we test these characteristics in the whole thing.
Yes. I guess a human can play in a dark arcade or a very bright arcade, and it doesn't really affect us, right?
Exactly.
So I imagine conventional algorithms and computer systems, they don't do so well with different lighting conditions like that.
Yeah, so the main problems with the conventional computer vision systems is if you train them to work in one particular setting, they just work in that setting, and when you change anything slightly in the environment, they start to fail. We want to overcome that by training it with different levels and also testing them in different conditions, so that we can confidently say that this system can work in these conditions.
So how does this relate to your PhD, though?
Oh, so my PhD project is to apply reinforcement learning on this pinball machine. So the aim of my project is to make the machine learn on its own how to play pinball without any human supervision, just by using the score as a teaching signal.
Okay, so you wanted to learn how to play pinball without anyone teaching it. It must learn from just saying, how do I get a good score?
Exactly. So that's how we learn as humans, right? So when we try to do a task, probably when I was young, my mom used to give me a chocolate whenever I used to perform better at whatever that I was doing. And that is a reward for me. And I try to get that reward again and again. So I repeat the tasks that I was doing, which used to give me the reward. And now the score of the pinball machine is a reward like that. And it has to just learn how to play these actions, left flipper or right flipper, and it just constantly looks for that reward. And whenever it gets that reward, it learns that, oh, doing this action at this point of time would give me a reward.
And forgive me if I'm jumping ahead here, but from what I remember seeing, you don't necessarily have to stick to the rules of normal pinball. You can change things up.
You got that right. We actually do a lot more than just playing with one single ball. We can add more balls for that matter, and it is extremely difficult for a human to play beyond 3 balls running around in the maze. And then, as you can see, there are a lot of distractors on the board. There are flashing lights. There are some places where the ball disappears and appears back again. So all of this adds up to that challenge, and it makes it more and more difficult to try to learn this. But we as humans are really good at it. So which is why we are trying to emulate the biological neurons in our brains and try to use those models to be able to achieve this sort of a robust performance on this machine.
It's an exciting project.
Yeah. Thank you.
So I have one more question for you, Yash, before I let you go.
Yeah.
Why is it important to teach machines and robots and neuromorphic systems to learn? Why is this something we need to do?
We are really good at dealing with a range of tasks and also being able to deal with that uncertainty in the environment around us. And it is very important for the robotic systems that we are building in this world to be able to be robust and be resilient to the changes in the environment. And as you can know, if you give a small 5-year-old boy the pinball machine, he will learn how to play pinball within 5 minutes maybe. But to achieve the same kind of performance, a machine or a computer might take much more longer time and data to learn these kind of things. So what we are trying to do is try to develop robust, resilient, and also quick learning algorithms which can work in this real world and also behave like or learn like humans.
Fantastic. So, do we have to worry about the robots taking over yet?
Just
We're a long way off, aren't we?
a long way.
Yes.
But you never know.
I'll keep my eye open.
Yeah.
Yes, thank you so much.
Thank you
That's
so much.
fantastic.
Thanks everyone.
All right.